Welcome. This is the second video in our series on apportionment, and in this video we are just going to present one method, Hamilton's method, to go through an example. And this is Alexander Hamilton, and so this method was developed to apportion the first Congress in the United States. But we're going to use the method to distribute social workers to 3 towns. So we have some county, and there's 3 towns. They have 24 social workers. They need to divide up those social workers amongst the 3 towns. You're thinking, okay, well, why don't they just give 8 to each town? Because 24 divided by 3 is 8. That'll be perfectly even. But the towns are not all the same. They have different caseloads. They certainly, almost certainly have different populations as well. And we don't have that information, but the measure that we're going to use to give shares to the different objects that we're distributing to, or the different recipients of the objects that we're distributing, will be the caseload. So in the apportionment kind of setup, our indivisible objects are the social workers. Our towns are the recipients, which are also undividable. And then the way we're deciding the relative size of those recipients is via caseload. So let's go ahead and go forward. So I'm gonna let me rewrite this table here. So town A, B, C, the number of cases, which is kind of taking the place of population, and 253. So the way the Hamilton's method starts is to go with the proportional route first. So the proportional or standard distribution, or quota. Standard quota. Not quotal. This is the proportional one. And the way that we're going to do this is find what's called a divisor, a standard divisor, that will represent the number of cases per social worker if everything were divided perfectly evenly. So if all the cases were divided evenly, then each social worker would take 41 plus 106 plus 253 divided by 24 cases. And the numerator there is the total number of cases, and the denominator is the total number of social workers. So let's go ahead and add those numbers up. 41 plus 106 plus 253 is 400 even. So there's 400 total cases. There's 24 social workers. And so that means that each social worker should get about 67 cases. That was if everything were perfectly equal. And what we can do with this number is we can divide it into the number of cases in each town and get the kind of ideal number of social workers. If we could break the social workers up into fractional social workers, how many each town would get, this would be the standard quota. So with this in mind, we'll take this in mind. Town A would get, so they have 41 cases, and we'll divide that by the 16.67 cases per social worker to get how many total social workers the town should get. 2.46. Town B would get So they have 106 cases. We'll divide it again by 16.67. So we should be expecting more than twice as many social workers. 106 divided by 16.67. And sure enough, 6.36 social workers. And then town C, should be 2.5 times this, about. $253. Yeah, okay. 15.24. Okay. So again, this is if we could divide up the social workers into fractional parts. This is the division we would choose, the apportionment we would choose. These numbers here in the standard quota column are proportional to the cases. So 2.46 is to 24, the total number of social workers, as 41 is to 400, the total number of cases. And you can see that pretty well. 41 is about 1/10 of 400, and 2.46 is about 1/10 of 24, slightly more than 1/10 in each case, because it's proportional. So this is where you start with Hamilton's method, and then the next step is to find the lower quota. So the lower quota just means round all of those numbers in the standard quota column down. So all via conventional rounding, all of these numbers would round down anyways, but in the lower quota, you're just writing out what's called the integer part. So what's the whole number? You just forget about the fractions for a moment. And then we look at the lower quota and we ask ourselves, okay, well, how many total seats, how many total social workers have we like distributed or given jobs to, or like told them where they're going to work? We say 2 plus 6 is 8. 8 plus 15 is 23. 23 social workers have been assigned. So we have one more social worker to assign. And the way that Hamilton's method works is it looks at the decimal part in the standard quota column and says, hey, who has the biggest decimal part? And you just read off, oh, the 0.46 is larger than 0.36, and the 0.46 is larger than the 0.24. So town A gets the remaining social worker. So Hamilton's method, Hamilton's apportionment, we'll give 3, 7, and 15. And now, oops, I did not add that up right. The 6 should still be a 6. 3, 6, and 15, there we are. All 24 have been assigned. So we can write down how that worked out. Hamilton's method awards the excess social workers to the towns with the largest decimals in the standard quota. And we only had one additional social worker. But if we had, say, only distributed 22 of the social workers after we had looked at the lower quota, then the next social worker would have gone to town B, because town B had the second largest decimal. So that's how Hamilton's method works. You look at the lower quota, and then you add up you see how many you've already distributed, and then whatever you have left over, you just go down in order based on the fractional part of the standard quota until you've given everybody away. And so in that fashion, you distribute all of your indivisible objects. So in future videos, we'll see some issues with Hamilton's method. But right now, it's just one method. It's the first method that we have on how to solve an apportionment problem. Okay, I'll see you in the next video.